P and T. The isothermal, isobaric. So that would be N, P, and T. And then finally the GC or grand canonical, which would be T, V, and mu. So what we generally want to do with these ensembles is use them to go from statistical mechanical space to thermodynamic space. So the general approach for that would be to try to take averages over some mechanical or extensive variable. So we want to perform averages over our ensembles, and that gives us our thermodynamic quantities. So what that looks like is we might say we want to take the average of the energy. And so we take a sum over all microstates of the probability of being in that microstate times the energy of that microstate. Where here I'm using J just to denote one state. And so how do we actually determine what this probability is? So kind of what we worked up last time was that we could say the probability of being in microstate J is related to the exponential of something related to microstate J divided by the sum over all microstates of that same exponential. So then does anybody remember what goes in this box? Kind of generally, no matter what ensemble we're in, does anyone recall what goes in there?
The terms you subtract for the Legendre transform?
Yeah, that's exactly right. So this would be, if we're doing the Legendre transform in entropy space, then the box needs whatever variables are fluctuating. And so we can write out what those are for each of these ensembles. So each of the ensembles, based on what are the control variables, that dictates what are the variables that can fluctuate in our system. So if we're in the microcanonical ensemble, so that's NVE. So remember, because the energy is fixed, we assume that all microstates have equal probability of occurring. And so the probability is just 1 over all those states. So it gets slightly more complicated when we look at other ensembles, but really it's just kind of adding one different exponential term at a time. So canonical is NVT, and so the probability is going to be related to the energy. And then finally for the canonical, now we just have energy that can fluctuate, but also particle number. And so we just include that again in the exponential. And we include that in the exponential on the numerator and the denominator, where this denominator is what we'll call the partition function. And then these additional terms, so one new term pops up for each exponential that we add. So this beta in the case of the canonical, or gamma in the case of the grand canonical, these come from the Lagrange multipliers, so solving these Lagrangian expressions. And so each of these partition functions nominally takes on a different exponential form and also takes on a different symbol. I'll try to stick to microcanonical is omega, canonical is Q. Probably won't get into isothermal, isobaric today, but then grand canonical, I'll try to use theta. But really these might turn into just being Q in the notes at some time. Just think that it's the partition function and remind yourself what are the control variables, and then the control variables. So the nature of the ensemble is what dictates what exponential terms are in the partition function. So we can also kind of relate these ensembles to one another. So for instance, if we tried to relate the microcanonical to the canonical ensemble, we can write the canonical ensemble partition function in a slightly different way. So let's say now instead of, so previously I just wrote it as the sum over all microstates J of this exponential of minus beta times the energy. But if I'm thinking in terms of the microcanonical ensemble, let's think instead in terms of summing over energy levels instead of microstates. So I can say that my canonical partition function Q of control variables N, V, and T is going to be the sum now over all energy levels E sub J of my microcanonical ensembles, and then again times this exponential. So then what do I do with this omega? How do I know what the distribution of states are in these microcanonical ensembles? Well, previously we kind of assumed that the peak in the distribution of energies is the one that dominates. So the state that has maximal probability of occurring is essentially the only state that matters. So then we can say that the energy equals this, sorry, there should be a sub J here. So the energy equals this E star. So this is just our maximally probable energy. And so we'll use that for all of our states J. So now we don't have to take a sum over all of these energy levels. We're just assuming that the only relevant energy is this maximally probable energy level. So now I can rewrite Q, removing the sum as just what is omega at this energy level, and then times the exponential of beta times that maximally probable energy. So I mentioned earlier that one way to go from statistical mechanical space to thermodynamic space is to take averages, but we can also go a different way, which is in principle the same way, but a bit of a shortcut, is we can take logarithms of the partition function with respect to some relevant conjugate variable. So we can say that, so to get into that space, let's take the log of Q equals now the log of this expression. So I can deal with what's on the right side of this expression and just say, all right, and if we kind of remember, or maybe this is starting to take a familiar form, if we divide through by beta, oh, sorry, let me see. One second. So we can start to see that this kind of looks like the entropy, right? So we know that S equals KB times log omega. And we can see that this is kind of starting to look like the Helmholtz energy. And of course, this guy, we're assuming that the average over the ensemble of the energy is equal to the thermodynamic quantity, which is the internal energy. And we're saying that the average energy, or assuming the average energy, is just related to this maximally probable energy, E star. So this gives us this thermodynamic looking expression. And we can actually show that this is exactly equal to F equals U minus TS. This is our characteristic thermodynamic expression for the canonical ensemble. So basically starting from a microcanonical ensemble, or our canonical ensemble in terms of this microcanonical ensemble, we can perform this workup and exactly get what is this characteristic expression for the canonical ensemble, showing that there's equivalence between microcanonical and canonical ensembles, just making sure that you properly account for states. So one thing that we did assume in this was that the only energy that's relevant is this E star. So this appears to show that microcanonical and canonical are equivalent because we can obtain this Helmholtz expression for the free energy from the microcanonical ensemble. But in reality, we made this assumption that all E's, or that the only relevant energy is this E star, but this is actually not the case for our canonical ensemble. So because the canonical ensemble does not have energy as a fixed value, these are not exactly equivalent. So we say that these are equivalent except for fluctuations in the energy. And I think most of this should be a recap from last time. So this just to kind of draw a cartoon that helps bring this in. If we're in a canonical space and we look at the probability of being in any energy as a function of that energy, then we get a curve that kind of looks like this. And so we assumed that the only energy that matters is this one. But in reality, there's some width to this, which is going to be equal to the standard deviation in the energy, roughly. So usually instead of standard deviation, we think about fluctuations in terms of variance. So this symbol just means the variance or the squared standard deviation of the energy. So now I'll go a little bit more into fluctuations. So we can write a general expression for the fluctuations of any extensive variable. So the fluctuations with respect to x are just equal to the average of x squared minus the average of x squared. And remember that anytime we're taking averages of some quantity, we can write that always as what is the sum over all of our microstates of the probability of being in that microstate times whatever we're interested in this case squared. So we're interested in x squared, so we have to take the probability of each state multiplied by that property squared. So I can also rewrite this in terms of partial derivatives. And excuse my lowercase x's, they're a bit outrageous, so it's just a squiggle. Okay, so then in the numerator of this expression is again just our extensive variable. And then this squiggle will be the normalized conjugate to that, the extensive variable that we're interested in the fluctuations for. So I can rewrite this as squiggle equals our conjugate y normalized by kt. And that's just mostly just for the convenience of expressing the fluctuations in terms of this simple partial derivative. So how do we think about what these fluctuations mean in terms of this partial derivative? So we're basically saying that the fluctuations equal the response of the average extensive variable x in response to perturbations of its conjugate variable. So basically, how does some mechanical property change as we perturb its conjugate? And so this manifests in some really physically meaningful quantities. So if we think about the canonical ensemble, we're usually interested in energy. So we know that the change in energy with respect to temperature, all else constant, and I'll probably get a little sloppy with my parentheses on these partial derivatives, but always, if we're taking the partial derivative with respect to one conjugate, then all other conjugate variables or control variables in the system are held constant. So we know that this equals the heat capacity. And again, this is this extensive variable divided, or the partial derivative with respect to its conjugate. And so that's also related to the fluctuations. And then with some KBTs mixed in. So we can do this similarly in the isothermal isobaric ensemble. And we get that if you take 1 over volume times the change in volume with respect to pressure, this is related to the isothermal compressibility of the system. And again, also related to fluctuations. So this is the fluctuation in volume divided by KT. And then similarly, we could say for the the grand canonical ensemble, we could take what is the change in particle number with respect to chemical potential of some species I. And again, this would be related to fluctuations in particle number divided by KBT. So in all of these cases, these look like something like capacities. So in the first case, we have the heat capacity. It's kind of like the volume capacity. How much is the volume going to change in response to changes in pressure? And this might be something like the chemical capacity. So as I change the chemical potentials in the system, how is the particle number going to change? So it's clear that these fluctuations are physically important, but how large are they? So essentially, how bad of an approximation is it to say that in the last example, for instance, that the energy just equals the most probable energy? So let's just get kind of an order of magnitude estimate on how large these fluctuations are. So the variance in the energy is going to be KBT squared times the heat capacity. So that means the standard deviation, or the width of that distribution in energy, is just the square root of that. And just for the purposes of order of magnitude analysis, if we have an ideal gas, then the energy is going to be on the order of NKBT. And the heat capacity, being the derivative of the energy with respect to temperature, is just going to be NK. So if we want to think about how large are the fluctuations, then the absolute value is not so important, but the relative magnitude is what's important. So if we say, what's the standard deviation in energy relative to the average energy in our system? So we can rewrite the standard deviation for the energy, subbing in for the heat capacity. So we did K T squared N, square root of that, divided by the average energy, which is, we're saying ballpark NKT. And so we cancel some like terms, and we see that the relative size of fluctuations is on the order of 1 over the square root of N. And so let's say we have about a mole of this ideal gas. So there's about 10 to the 23 particles. And so the relative size of this fluctuation is very small. Just about 1 over a trillion. And again, this is the relative size. So it's kind of the percent of the total energy that's fluctuating. And so that's an extremely small number. But they're still important because fluctuations give rise to these capacity-like terms that we can derive, or that I showed just a second ago. Are there any questions at this point? Are we all good? I think this is all recap. Cool. All right, so then just a quick note on taking these averages. So these kinds of taking the average of something squared or the average of something and then squaring it. Just remember that the average of some function is not necessarily equal to that function evaluated at the average value of the independent variable. So I can show this if I just take a simple example. If f of x equals x squared, and I say my x could be 0, 1, or 2, then the average value of f of x equals 5/3, whereas the average, or f evaluated at the average value of x, would be f of 1 equals 1. So just be careful and don't assume that you can do this, although for some functions you can. All right, so then one more example with fluctuations, and then we'll move on to some new stuff. So and you'll get to see some of my iPad drawing skills here, which are not so great. All right, so fluctuations actually play a role in how we perceive the color of the sky. So there's a phenomenon called Rayleigh scattering. Which basically says that if light incident with some wavelength, where the wavelength is greater than the particle it's incident upon, then the light will scatter. And then the actual details of all of these equations are not super relevant for your course, but I'll just go through them. So we can say the intensity of scattered light incident with some angle theta is going to be equal to the incident intensity times this term, pi squared, times the volume of atmosphere it's going through, times the fluctuations in the dielectric constant, divided by 2 times the wavelength of light to the 4th, and then times some term that accounts for us being incident on a sphere. So the important point here is that the intensity of scattered light is going to be proportional to the fluctuations in the dielectric constant. So if there were no fluctuations in the dielectric, then this term would go to 0 and this whole expression would go to 0, and none of the light would be scattered, even as it's incident upon particles in the atmosphere. So as with any fluctuation term, I can write the fluctuations in the dielectric like this. And then it's known that the dielectric constant of some system is proportional to its density. Where A is just a constant, kind of like polarizability, or it accounts for the polarizability of the particles in the atmosphere. So this tells us that fluctuations in the dielectric are going to be proportional to fluctuations in the density, which we can say in terms of kind of fundamental quantities that's proportional to fluctuations in the volume. And if we remember before, when we're dealing with fluctuations in the volume, that means that we get this term isothermal compressibility is going to come up. So without going into all of the details, which are not super important, we can show that this intensity is then related to the incident intensity, pi squared KT, divided by wavelength to the 4th, isothermal compressibility of the atmosphere And then these terms that arise from converting from dielectric to density. And then all of this again times this cosine theta term. So then we integrate this to determine the total intensity of scattered light. So this is a function just for a given angle of incidence theta, but we need to look at all angles. So we kind of integrate over the sphere. And eventually we can show that, let's get it. The intensity of all scattered light is a function of the wavelength of incident light, 1 over that to the 4th power. So this means I scattered is proportional to lambda to the -4, where lambda is the wavelength of light. And so again, it's important to note that this whole relationship just arises because the fluctuations in the dielectric constant of the atmosphere are non-zero. All right, so how does this manifest in the colors of the sky? So obviously light is incident upon the Earth in a number of different wavelengths, ranging from low wavelengths being blue or purple light, high wavelengths being red light. So let's see if I can draw this. So if we imagine a situation, let's say at about noon. So here, I'm going to be on the Earth here. Let's see. And then there are all of these gas particles in the sky, right? And so what happens when red light is incident upon this atmosphere, it doesn't scatter very much because the intensity of scattered light is proportional to lambda to the 4th. So our long wavelength red light kind of passes through. So if it happens to, if I look directly at the sun, it will pass through and hit me, but it's not being scattered into my line of sight by the gas particles so much. Whereas if I have blue light, what's going to happen is, you know, this ray of light initially didn't look like it was coming my way, but then it starts to scatter off of all of these gas particles and eventually finds its way to my face. And so that's why if you kind of look at the sky at noon, then the sky is very blue. So now if I change this, change the time, and now the sun is really far away, let's say at dusk. Then the atmosphere is much thicker that it has to go across. So I have all of these gas particles everywhere. And so the only light that's actually able to make it through are the long wavelength lights, rays of light that don't scatter so much. So red light kind of makes it through and I see it, whereas blue light kind of just scatters away and doesn't make it all the way to my eyes. And so you might say, well, blue light is actually not the lowest wavelength light, so why is the sky not purple? This really has to do with one, the intensity of incident light is specific to the sun. So the wavelengths of light that the sun is actually emitting are slanted towards blue and not purple. And then our eyes are also just more sensitive to blue. So if our eyes had a slightly different chemistry, we may see more purple light. All right, I hope you enjoyed my artistic wanderings. I'm sure Garrett is jealous of all the different colors I can use on my iPad. So maybe I'm jealous of his whiteboard, but I have all these different colors to make him jealous. All right. Thanks for the applause, appreciate it. All right, so are there any questions on fluctuations? This is kind of the end of the review, and now we'll go on to some new stuff. So fluctuations are kind of the general way that we we get probabilities or average quantities, or are we all set? All right, sounds good. So I guess one more semi-review is just how do we solve problems in StatMech? So the first thing, we need to find the states, microstates. So I know Garrett uses nu, I tend to use j, mostly the same difference. Once we have the states, we find the energies, so it'd be E sub j. And then we need to know all of the states, so find the partition function. So maybe this is Q or theta or what have you. So how do we actually find the energies? This is not so trivial. So imagine we had n particles. Then that means we need to solve the Schrodinger's equation for all n of those particles simultaneously. So we have some Hamiltonian that acts upon the wave function of this entire n-bodied system. And that's really the only way we can definitively get exactly what is the energy. And so if y'all have taken any kind of physical chemistry or intro to quantum mechanics, you know that we can only solve the Schrodinger equation for maybe one particle or a very simple system, but we certainly can't do it for 1 mole of particles all at once. And so we can't do this for an n-body system where n is anything reasonably large. So we're kind of stuck here on step 2, but fortunately, for the sake of statistical mechanics, we can make some assumptions. So our way out of this problem is to assume that our particles, or more generally, our degrees of freedom, are behaving independently. So now I can rewrite what was initially just one Hamiltonian that contained all the degrees of freedom in my system. I can now break up this Hamiltonian. For instance, if I had a single gas molecule even, so it doesn't have to be breaking up the Hamiltonian in terms of particles, but it can be in terms of different contributions to the energy. So I might say the overall Hamiltonian is a Hamiltonian for translations, +1 for rotations, +1 for vibrations, and so forth. And so my assumption here is then just that translational Hamiltonian is not it behaves independently of the rotational Hamiltonian and so forth. And so again, this could be degrees of freedom, or it could be particles being separated here. And so the powerful thing here is that because I've separated my Hamiltonian, then by definition, I've separated the energy as well. So the total energy of the system can be broken up just like the Hamiltonian. And so this is then much easier because now we don't have all of our degrees of freedom lumped into a single equation, and we can separately work on solving this equation and solving that equation and solving that equation. It's a much simpler mathematical system to work with. All right, so now let's do this for particles in the canonical ensemble. So let's say we have a canonical ensemble of particles. Then, as per usual, we write the partition function for this. Summing over all states j, just the exponential of what's left in the Legendre transform, which is beta times the energy. And so let's say that these particles are independent, and we can distinguish them. So I could look into this box at any time and say, okay, that's particle A, that's particle B, and so forth. So if this is the case, I can rewrite the partition function. By dividing up this energy and also dividing up each of the states. So I can say this is the exponential of beta times now these single particle energies, E or small epsilon sub I for particle A, epsilon, so the energy of state J for particle B, and so forth. So then I can also divide this, because it's exponential, sums in the exponential, I can rewrite this as a product of sums. So I could sum over all of particle A's states, multiply that by all of particle B's states, and so forth. And so I can only do this again because we've assumed that these particles are behaving independently. And so what this means is I have now these single particle or molecular partition functions. And then my total partition function is just the product over all of these. So then I can write Q as, or big Q is just equal to little q for particle A times little q for particle B, and so forth. So rewriting that in product notation. For each of my particles, here I'm calling a particle nu. I just take the product of all of my particles from 1 to n, or the molecular partition function for each of those particles. So now again, we're usually interested in some extensive quantity like the energy. So the average energy of the system is still equal to the log of the partition function relative to its conjugate. So again, this is the total partition function. But now I've said because this big Q can be divided into the product of all of these small q's, and then that means I can also divide the energy now into a sum. And so this equals my little q for A minus d log q for B, d beta, and so forth. Where then each of these guys are just the single particle energy. So I can rewrite this as the average energy for the entire system, so the internal energy is just the sum of these single particle energies. So we have something that was an n-body problem is now n one-body problems, which is much easier to solve. Now we can make one more simplifying assumption. If we assume that the energy levels accessible to each particle are the same, that is QA equals QB, or it has the same form as QB and so forth, then we can just write that the big partition function over NVNT is just equal to the small partition function, which again is just now a function of volume and temperature raised to the n. So that allows us to remove this index where we're always keeping track of A, B, C, and so forth, because the energy levels accessible to each particle are the same. So recall that to get to this point, we assumed that the particles were distinguishable. So even though they have the same energy levels, we can look in the box and see this is particle A, this is particle B, and so forth. So what if we remove this assumption and say that the particles are indistinguishable from one another? So then if they're indistinguishable, you might have the notion that this is overcounting. So that would be correct. So Q to the N, this overcounts. And so we have to divide by something, but it's not clear immediately by how much. So just to give you an idea of where that overcounting comes from. So let's consider a system with two particles that can be in two states. So let's say my particles are A and B, and my states are 1 and 2. So state 1 might look like this, state 2 might look like, oh boy, more drawing skills. And state 2 might look like that. So if my wave function for these particles is symmetric, then I have bosons. And don't worry if you're not exactly following what I mean by wave function symmetric and bosons. We'll go into that in much more detail. So if my wave function is symmetric, then there's no limitation to particles occupying the same state as one another. And so this is the set of states that my particles can be in. So both A and B could be in state 1. A could be in 1, but B in 2, the reverse. And then they could both be in state 2. And then alternatively, if I'm anti-symmetric, and that means I have fermions. And so fermions, you can't have two identical fermions in the same in the same state. And so that just restricts my set of allowed states to be A in 1 and B in 2, or the reverse. But remember that for this system, I can't tell the difference between A and B because they're indistinguishable from one another. And so I don't really have 4 states for bosons and 2 for fermions. These two are equivalent in both cases. If I can't tell A and B, then I just know I have 2 particles. One is in state 1 and one is in state 2, but the order of those is not relevant to me. So if we think combinatorically about how this is then overcounting, so correcting for this overcounting, n particles can arrange themselves in n factorial ways. And so I just divide q to the n divided by n factorial. But this also makes an assumption. It assumes that every single particle has its own state. If this is not the case, then dividing by n factorial is actually over accounting for the double counting of q to the n. So we call this approximation Boltzmann's approximation. And we think about when Boltzmann's approximation is valid, we're in a quote unquote classical regime, or we're applying classical mechanics. So because this is the case, this approximation holds as long as the number of states available is much greater than the number of particles. So you can imagine if I had 1 billion times as many states as particles, then it's a pretty decent assumption that each particle is going to be in its own state. Whereas if I have a small number of states relative to particles, then that approximation or that assumption gets a bit trickier. All right, so let's take a look at when this might be valid. So let's take a system of particles in a 3D box. All right, here we go again. Once again, I'll try to draw something. All right, so here's our box. It's a cube with length A, and it has some monoatomic particles in it. So then the parameters of this box are A is 10 centimeters, temperature is 300 Kelvin. The mass of the particles is on the order of 10 to the minus 27 kilograms, which is about the mass of hydrogen. The pressure, 1 atmosphere, and then the energy will take to be 3/2 kT. So then from this kind of classical quantum mechanical example, we know that the number of states at a given energy is going to be pi over 6 times 8 times the mass of the particles times the length of the box squared times the energy divided by Planck's constant squared, and then all of this raised to the 3/2. So if we plug all of that in, then the number of states up to our energy of 3/2 kT is on the order of 10 to the 30 states available to these particles. And if I take this to be an ideal gas, then my number of particles is, of course, PV over RT, and this is on the order of 1 mole of particles. So this is good for the purpose of Boltzmann's approximation. So phi is much greater than n. So we are in a classical regime. And we can apply Boltzmann's approximation. All right, so based on this kind of simple example, can anyone tell me when Boltzmann's approximation becomes good or becomes bad? So kind of what are the handles that we might look for that suggest whether Boltzmann's approximation is going to be valid? So maybe, yeah, let's say when does Boltzmann's approximation get better, kind of looking at this system? Anyone in the audience? So we can think that we want the number of states to be better than or higher than the number of particles. And so the number of states that our system can explore, this increases with temperature. And then the number of particles in our system decreases, or it increases rather, with density. And so Boltzmann gets better for high temperature or low density. Whereas if we're at the opposite of these regimes, then we can no longer make the assumption that every particle is in its own state, and then we're in more of a quantum regime, which I'll get into, I think, by the end of this lecture. All right, so let's apply Boltzmann's approximation to some system. Let's see. Okay, so if we have n particles, each has some set of allowed energies, so possible energy levels. What is the average energy? That's essentially the problem we're trying to solve. So we can write out the partition function in terms of Boltzmann's approximation. So this is the big partition function Q equals our molecular partition function raised to the number of particles. And then to correct for overcounting, assuming that every particle can be in its own state, we divide by n factorial. So recalling what our molecular partition function looks like. So that would be the sum over all energy levels, or the sum over all microstates I, e to minus beta times the energy of that microstate I, and then all of that raised to n. So let's assume that these particles not only are independent, which is required for Boltzmann's approximation, but also identical. And then we can write that the average energy just equals the number of particles times the average single particle energy. So that's the total energy is just related to the average single particle energy. So kind of once again, the way we're typically bridging the gap between thermodynamics and statistical mechanics is to take the log of our partition function with respect to a conjugate. So for the canonical, that's usually Q with respect to beta. And our statement here tells us that we can just break this up into, say, n times the log of our single particle partition function with respect to beta. So this tells us that our total energy is just n times this average energy. So the sum of probability times epsilon sub I. So that means to get the total energy, if we have independent and identical particles, all we need is this single particle energy. All right, now let's think about fluctuations one more time. But now we're thinking about these single particle energies. So let's think about fluctuations just for these single particles. So if we recall that in terms of the total energy of a system, this was on the order of 1 over the square root of n, the relative size of the fluctuations in the total energy for a system of n particles. And so this is very small. But if we're now in a single particle picture, fluctuations can become much more important. So let's show that for each particle, my fluctuation in the single particle energy is again the partial derivative of the average single particle energy relative to beta. So this is going to be 1 over n times the partial derivative of the total energy with respect to beta. And we remember that that is related to the heat capacity. And similarly, we can say that our average energy, so again, to get the magnitude of relative fluctuations, we want the standard deviation in the property with respect to the average of the property. So what's our average energy? It's going to be the total energy divided by the number of particles. So in our last example, I think we took the average energy to be nkt as an estimate. And so now if I take the square root of this fluctuation expression and divide it by the energy, I get kt over kt equals 1. And so the relative fluctuations are very large for single particles. And it's only when we have a system of very many of these particles that the fluctuations eventually go to very small numbers and approach 0. So if we have n particles, the relative fluctuation is about 1 in a trillion. Whereas if we have a single particle, then the fluctuation is the magnitude of the energy itself. All right, so what if Boltzmann's approximation doesn't work? This might be when the number of states is kind of equal to the number of particles, which might be low T or high density among some other different parameters. So now we can't say that Q is just the single particle partition functions to the n divided by n factorial. So we'll call this the quantum regime as a contrast from the classical regime where Boltzmann's approximation is valid. So for the quantum regime, we want to think in terms of occupation numbers. So that basically means that we have some energies that are available. So I have a set of energies, E1, E2, and so forth. And then each of these energies has some occupation. So some number of particles that are exhibiting that energy. So then I have a set of occupation numbers like N1, N2, and so forth. So this introduces some constraints. So I know that the total energy is going to be equal to the sum over all of my states times the occupation number of that state, or of the occupation of that state times the energy of that state. And then also the number of particles in the system. Basically every particle must be somewhere, so my sum of occupation numbers must go to the number of particles. So these are the constraints on the system. And what these constraints basically do is impose an interdependence among the occupation numbers. And the way to think about that is, let's say I have 5 particles and I know all 5 particles are in state 1, then by definition I have 0 particles in state 2 and 0 particles in state 3 and so forth. And so by defining the occupation number of some state, I'm also implying the occupation number of other states. And so that creates this interdependence created by these constraints. So we could use any ensemble to think about this system, but it happens to be that dealing with these constraints is most convenient in the grand canonical ensemble, and so we'll use that one. And so we're really just trying to figure out, now that we're in this quantum regime, how do you define the total partition function of the system? And then once you have that partition function, what can you do with it? So we have a grand canonical ensemble, and our system is really defined by what is this, the set of occupation numbers. So which particles are in which energy levels. So I could write that my occupation number in state I is some function of my overall system variables. So this here I'm saying the occupation of state I, is that occupation subject to the constraints of my system? Basically, given an entire system that's in system state nu, I have some set of occupation numbers for each individual single particle state I. So I can start by writing my partition function in terms of this system state. So summing over all states of the entire system, I know for the grand canonical ensemble, that's exponential of minus beta, the energy of that state minus the number, mu times the number of particles in that state, where mu is the chemical potential. So then I can write the probability of being in that overall system state nu is just the exponential of that quantity divided by the partition function. So this still holds and this is true, but we know that our system is really defined by these occupation numbers, and our occupation numbers don't appear in this expression, and so it's a little hard to work with. So then our goal is to try to convert this system level view into an occupation number level view. So first we'll consider we have bosons. So bosons have symmetric wave functions, and what that means is there's no limitation to how many particles can be in any one state. So that means our occupation numbers span 0 to infinity. So instead of summing over our potential system states, let's sum over all possible occupation numbers. So let's rewrite our partition function. Now summing over n sub I. So here I've rewritten this because, or I'm allowed to do this because I have my constraints that the overall system energy is just the sum of the occupation numbers times the energies of those single states. And then the number of particles in my system is just a sum over all my occupation numbers. That's why this sum appears now in the exponential. So on the downward sum, I'm summing over different sets of occupation numbers. And in the sum that's in the exponential, I'm summing over states. Now I can rewrite this. In terms of a product, because I'm summing in the exponential, I can always convert that into a product. So I'm taking the product over all states I from my occupation of state I going from 0 to infinity times the exponential of minus beta times this single particle picture here. And I can rewrite this slightly to say that, again, theta equals the product over our microstates I, summing from the occupation of I going from 0 to infinity. And then just kind of popping this n out. And then the reason I do this is because if I take what's in the parentheses here, now this has the form of summing from 0 to infinity of x to the n. And this is a known infinite sum of just 1 over 1 minus x. So if I take what is x in this situation, my partition function then becomes the product, again, over all microstates I, of 1 over 1 minus x. So again, this is the total partition function for bosons. And then what's in the parentheses here would be my single particle partition function. So again, I have this kind of form that's like the total partition function is the product of single particle partition functions, but I just have to do this workup in order to figure out what's the form of the molecular or single particle partition function. So we have theta. So now let's think about what is the, let's go back and now think about what are our occupation numbers. So we have theta. How many particles do we have in a given state I? So I know that my average number of particles in the system is going to be a sum over all of these average occupation numbers. Basically, all of my particles are somewhere. So again, to kind of transition from StatMech to thermo, we need to take some partial derivatives of the log of the partition function with respect to some conjugate. In this case, we write the average number of particles in the entire system in terms of the partial derivative of the log of our partition function with respect to the chemical potential mu. So we can do a bit of math to show that we take this log and partial derivative. I guess I'm not taking the partial derivative just yet, but take out beta. So I'm essentially just rewriting or subbing in this expression for theta. Now, because I have log of a product, I can convert that into a sum. So now I'm summing over all states I. Now the log of this expression for the partition function. Now taking the partial derivative with respect to mu. I get this expression. And so remember that we're after the single particle or the occupation number here, not the total number of particles in the system. But if we recognize that here I'm taking the sum, here I'm taking the sum, I'm summing over the same thing. And so what's inside the summation is just equal to our average occupation number of state I. And then this is called the Bose-Einstein equation. And it applies to bosons. So we can think about how does this equation behave, or how is the occupation number for bosons behave as a function of some conditions. So if my energy is much greater than my chemical potential, then this average occupation becomes like this. So I'm basically removing mu from these expressions. And if my energy is much greater than the thermal energy, kT, factor, this is just Boltzmann. So what does this say? So my energies are very large. So that implies high T, or that at least implies many states. And so it's not surprising that given a system where we have many states, by stating that the energy is much greater than mu and that the energy is greater than beta, the implication is we have many states. And so because we have many states, we can apply Boltzmann's approximation. And so we get the same thing whether we apply Boltzmann's approximation early on or get the Bose-Einstein statistics, assuming a quantum regime, but then make these simplifications. So if we have an alternative case where the energy and the chemical potential are similar, then we get what's called a Bose-Einstein condensate, where all of our particles condense into a single state. It's basically the occupation number of a single state goes to infinity. And then there are different kinds of bosons. So we could have non-conserved bosons, where mu is 0. So these would be like photons and phonons, where we don't necessarily have to have a one in, one out type situation. And then we could have conserved bosons. And here these have mass, so these might be atoms or molecules, and then the chemical potential is non-zero. All right, it looks like I have a few minutes. I think I can get through fermions. Okay, so if we recall, sorry, I just scrolled on you when you're probably writing, but so we recall that we made this an infinite sum here for bosons. So for fermions, our occupation numbers are capped because we cannot have two particles in the exact same state. And so that's really the only difference here. So now we have fermions, which the max occupation number is 1 instead of infinity for bosons. And the way that manifests is now we take the same expression I wrote previously. So the product over all microstates I from the occupation of that state going from 0, but instead of infinity, now we're going to 1 of the exponential that we wrote before. So now I don't have to do the same trick where I said the sum of x to the n is 1 over 1 minus x. I can actually just evaluate this sum. So at ni equals 0, this just goes to 1. Then at ni equals 1, this just goes here. So now I'm just plugging in the values for that sum at occupation of 0 or occupation of 1. Then kind of following a similar workup as before, if I want to know the average number of particles, once again, I say the average number of total number of particles in the system is just the sum over these occupation numbers equals kt log of the partition function log of mu. And then eventually I get, following a similar workup to before, an expression that looks like this. So it should be plus. And so this should look familiar, I hope. So this is essentially the same thing as the Bose-Einstein equation. This is called the Fermi Dirac. So I can say that the average number of particles for a Fermi Dirac or Bose-Einstein system is just 1 over beta times E minus mu plus or minus 1, where it's a plus for Fermi Dirac and it's a minus for Bose-Einstein. And so this difference just arises because we take our occupation number sums to different numbers. So this would be the only difference in the two workups is how many particles can possibly occupy a given state. And so just very quickly, what do these distributions look like? So here's the probability, or equivalently the average occupation number of some state as a function of this quantity beta times the energy minus the chemical potential. So if I have a Fermi Dirac distribution that looks something like this, where this is 1, so the average occupation number for fermions cannot exceed 1. Then for bosons, I get a different picture that looks something like that. Again, you can appreciate my drawing here, where I get a lot of occupation at low energies, but then not as much occupation at high energies. And then a Boltzmann distribution actually looks pretty similar to a Bose-Einstein, just slightly shifted. So a key thing to note is that all of these become similar at high enough energy or high enough temperature. But that the magnitude of energies explored by bosons is generally much lower than by fermions, because fermions are constricted to this, the average occupation number cannot exceed 1. So as I add more particles to the system, they necessarily have to go to higher and higher energy to fill those states. All right, that's all I have for today. Sorry for keeping you a couple minutes extra. And then if anybody has questions, I'll stick around for a little while, but otherwise I'll see you on Wednesday.